Hello everyone, and welcome to today's webinar. My name is Marco Perez with the Modal Shop, and today we're going to talk about vibration shakers, understanding the basics. Going to review how shakers work, how they are designed, and how that design has evolved over time. What are the key specifications and things you need to look for when you're selecting the right shaker for your application. So when we're talking about shakers today, we are talking about electrodynamic shakers. There are many types of shakers. You can have mechanical shakers, hydraulic shakers, and electrodynamic. And electrodynamic shaker, we have a magnetic field and an alternate current that runs into that magnetic field, creating an electromagnetic force that's alternate following the current that is driving the shaker. So small size shakers typically are designed using permanent magnets. As you go into mid and large size shakers, instead of using a permanent magnet, we substitute that with a field coil to create an electromagnetic field. The nice thing about shakers from a testing perspective is the fact that they are a great tool to provide controlled and measurable excitation input that you can apply to a test article or a structure. It could be a product, it could be like an airplane or an automotive body. There are many applications out there that we can cover using electrodynamic shakers. The basic equation for the electromagnetic force is simplified and written down there. The force is proportional to the length of that wire in the magnetic field, the magnetic field itself, and the current that's being delivered to the shaker by the shaker amplifier. And in the mechanical world, F equals ma, so that electromagnetic force will translate into an acceleration, velocity and displacement, and a movement, the vibration, oscillation of the shaker. So a shaker works pretty much like a loudspeaker, and in that way we've seen many people attempting some homemade designs where they were starting from an existing speaker and trying to shake something. The challenge here, and I don't recommend you to do this at home, is the fact that speakers are designed to produce sound waves. So you're trying to pump air, and when you're doing vibration testing, you're typically interested in optimizing the force output of your shaker. So in this example right here, the homemade designer kind of struggle a little bit with the payload. We had this little circuit board they're trying to shake, and it's too heavy for the speaker, so they're trying to suspend it and come with some very creative tubing and spring architecture here just to suspend and trying to counteract the weight of the payload. This is another example of a homemade design. So again, if you are looking at a shaker, if you're looking at vibration testing, the nice thing to do is to look at a professionally designed electromagnetic shaker. And here's a good example here where we are trying the same type of testing. This is a university research where they are trying to simulate and shake some peacock feathers. The first attempt by the professor, was using a kind of a speaker-like exciter, and the amount of force was very limited. You could only shake one feather. Then the next step on the experiment, they substitute the speaker-like shaker with a professionally designed shaker, and of course the force output was much higher, and they were able to simulate and shake multiple feathers at the same time and trying to reproduce the dancing, the mating dance of the peacock, and that was kind of the purpose of the research there. So we are going to go into how shakers are made and designed and how we can optimize that design for different applications out there and how that design has evolved over time. And if you go into the web, or if you go into different catalogs and different manufacturers, you're going to see shakers come into different colors and shapes and in slightly different format, but essentially the basic principles are the same as we explained earlier, an electromagnetic field. And the part of the design challenges that we encounter when designing a shaker are listed in the following slide. And one of them is the overall size and weight. Of course, you want to optimize and maximize force. You can do that by using a bigger magnet, making a bigger shaker. So you're trying to optimize force while still keeping the shaker at a reasonable size. And in a lightweight shaker is preferable, for example, if you're doing a modal testing application. So it's much easier to move the shaker around and install it and connect it to the structure. If you have to move the shaker to a different location, you don't need a forklift or like 3 people to move that around. When you're looking at the components of the shaker, for example, the moving part of the shaker, the armature, you're looking at things like the mass of the armature itself. You want the energy of the shaker to be delivered to the test article, but the shaker has to move itself, so you want to minimize that armature mass most of the time. The magnetic circuit, how do you make that circuit more efficient? How do you get more of the field into the shaker coil, into the armature coil? Of course, you want the shaker to be safe. You want it to be easy to use. So you got to combine all those challenges. You got to look at all the different applications out there where you can use a shaker, and which design characteristic is more important for this or that application. So a few examples here, like let's say if you're calibrating a sensor, you're calibrating an accelerometer, it might be interesting to you to have a very good low frequency performance if you're calibrating a seismic accelerometer. And to get to those low frequencies, you may want to have more displacement on your shaker. You may want to, for example, for modal testing, you want to make it easy to the user to connect the stinger and the force sensor and attach that to the structure. In an industrial application, you want the shaker to be robust and portable, same as if you're using the shaker at a university, in an educational lab. You want the shaker to be rugged and survive and be student-proof and be available for many, many years to go. So again, we're going to look at each one of those desirable features depending on the application, and highlights how we handle those characteristics over the years in the different designs. So back in the days, and this is something that Wayne Tusting, some of you may know him. He exchanged a few emails with me a few years ago, and he talked about his experience back in the late 50s, and they were testing aircrafts at the time, and there were not many options to choose from. Shakers were very big, more than 100 kilograms each one. They needed, more than one person to position it with the airplane, and that was it. We didn't have many options, and the amplifiers were also huge. They had tube amplifiers and so on. As things evolved over the years, jumping to the 70s, and this is a particular shaker that called my attention. I think it was, that was first, they first published a paper on this in 1971, and this shaker used the same driving mechanism. They had the coil, a common base, And what they did, they designed several different heads that were interchangeable, and each head was optimized for a particular application. So they had, for example, the big table head, obviously had a large mounting top or mounting area for testing different articles. But of course, that adds mass to the table. So if you're trying to do like a high G, maybe you want to reduce that mass and make it a smaller table. They had a general purpose table. They had also a table that was optimized for modal testing. That had an additional coil length, and it could get to a higher displacements. So each one of these tables was optimized for a particular application. You couldn't do it all with just one configuration, or perhaps the general purpose head was kind of a middle term for that. So that was a clever solution, but of course, probably not the most cost effective, because you had to have multiple heads to be able to tackle all the different applications. Moving along, so let's look at one particular very popular application, which is modal testing. And with modal testing, a few of the things that are desirable on the shaker design is make sure that it's easy to use, make sure you have enough stroke, especially if you're testing large structures and low frequencies, and also keeping the armature mass lower. It's also a desirable feature. So the first thing that was introduced in the late 80s was the through-hole armature design. So with this kind of design, basically the shaker has a through-hole which allows for an easy stinger attachment. The stinger can slide through the shaker body and be attached to the shaker, or by this just a chuck and collet system that basically grabs the stinger in its place. And it's easier to explain that by just looking at a short video we have here. I hope that shows correctly through the webinar. So we're going to have a 30 seconds video here that it shows the stinger. Basically you're sliding the stinger through the shaker and connecting it to the sensor that's already installed on the car side. I'm going to show that again just to be sure we capture that on the recording. So again, the shaker has a through-hole armature, and you're first connecting the stinger to the sensor that's on the structure. Then you lock it up in place, and then you lock the chuck on the shaker end, and now you're good to go. So that shows you how quick and easy was the installation of the shaker. If you look at the traditional table design versus the through-hole design for different shakers, here's an example. I have on the left the red shaker. It's not a through-hole armature, so I have to have a stinger that has the exact length. The distance has to be exactly the distance between the shaker table and the bottom of the car in this case. So that can be sometimes a little complicated. You may have a stinger that's too long, then you have to cut it shorter. If you cut it too short, then you have to either move the shaker up or move the car down. You don't always have that luxury. It's just, takes more time, makes it a little bit more difficult to set up the shaker to the structure. On the example on the right, on the blue shaker, we had the through-hole armature. So it's just like we saw on the video. I can easily get to the sensor that's under the airplane wing and lock it up in place. I don't need to have the exact stinger length in place, because I have a little bit of extra stinger that is just inside the shaker body on the right. Also, the fact that I have a little shaker table on a traditional shaker adds more mass to the armature, and And if I have less mass on my armature, that reduces some of the force drops at resonances when I'm doing modal testing. Moving on other improvements that are directly related to the shaker design, a lot of the small size shakers, they use a permanent magnet. So if we look at the magnetic circuitry, the key component is the magnet itself. So in the early modal shakers, pretty much the only option were all nickel magnets. It's an alloy of aluminum, nickel, and cobalt. Those magnets had a certain they could generate a certain magnetic field, and to get to the forces that we wanted, we had to use larger magnets. So that kind of made the shaker heavier and less portable. And you also had, a high magnetic field around the shaker, which is not the most desirable thing to have if you're testing something that can be susceptible to the magnetic field. So you can see here like the tools are attracted to the shaker through the big magnetic field, because basically the magnet size is basically the diameter of the shaker. Around I think the late 90s, rare earth magnets became readily available, and they start to substitute the all nickel magnets on the shaker designs. So the main type of rare earth magnet is called the neodymium magnets. And what it does for you, you can have I would say 3 to 4 times the amount of magnetic field for the same size of magnet. So that allows for a much more compact design, and you have much more magnetic force, and you can keep that magnet inside the shaker. So you have much less magnetic field around the shaker where you don't care. And just for the sake of comparison, I did a little search on the internet for a couple of shakers that had approximately the same force range. So the shaker on the top, had the 311 newtons of force with cooling, and that shaker weighs about 82 kilograms or 181 pounds. So the shaker on the bottom has basically the same force rating, 334 newtons, and only 16 kilograms. So it's a fraction of the size and weight of the shaker on the top, and that is primarily due to the smaller size magnet. Also, I think the base on the red shaker is also more massive. But if you keep looking around, this is another example where the tritium base is about the same style, perhaps the same mass, but the shaker on the top is 36 kilograms, which is almost a little more than twice the mass of the shaker on the bottom. So so basically any new design nowadays, we would prefer to use a neodymium magnet or an electromagnet if it's a larger size shaker. But for the smaller shakers, definitely neodymium magnet as a permanent magnet choice. Okay, talking about size and weight. We also had an interesting evolution when it comes to the amplifiers. So traditional shaker amplifiers were linear amplifiers. Nothing wrong with that. I mean, those are good amplifiers, but they tend to be not as efficient, and so a lot of the energy is actually turned into heat instead of being delivered to the shaker. And so you could see some of the common elements you see on those amplifiers. You can see some large, like a heat sink on the back of the amplifier. Also, the internal components on the amplifier make it a little bit more heavier. So this particular amplifier weighs about 9 to 15 kilograms, which is about 2 to 3 times the weight of a modern Class D amplifier. And because amplifiers nowadays can be much more efficient, they can also be made much smaller, So we have here one example where we were able to design a really tiny amplifier that would fit right underneath the shaker. So we are able to get a shaker and amplifier in one package, which it's very portable, very compact, very easy to use, and a lot of people appreciate that kind of design. So you don't need any more like a bulky and large amplifier next to the shaker, not necessarily. So those things are possible using Class T type amplifiers, which are very common nowadays. You know, your cell phone would use a Class T amplifier. You know, a lot of the electronic devices that we see around us, the smart speakers, they all use, you know, this type of amplifiers. Looking a little bit deeper inside the shaker and some of its internal components, I want to highlight a little bit about the suspension systems. You know, the suspension system keeps the armature of the shaker in its place. It aligns the armature as the armature moves up and down through the gap, and it also holds the armature at this middle position so where the shaker can go up and down. So this particular shaker design, the one on the left, the one on the right, you know, you have this double layer FLEXURE-based system, which is pretty common. And one thing that's interesting, you know, you can design that FLEXURE system in different ways using different materials. So one thing we like to use in some of our shakers are carbon fiber FLEXURES. And one benefit of that is a very rugged material, so it's really, really hard to break. I have an example on the bottom where, you know, it's a typical phenolic type of FLEXURE, kind of like a spider suspension you'd see in a lot of the small shaker designs, and that's a nice lightweight design, but on the other hand, you know, you may sometimes a little fragile, and it can break after too many cycles, you know, a little fatigue on the FLEXURES. They're relatively easy to break, especially because if you're mounting things on the shaker all the time, you're applying some torque on the whole armature. That torque is transmitted to the suspension system, and eventually you can have a small crack, and as you're shaking, you know, that crack over time we end up having a failure on the suspension system. So the carbon fiber materials are nice. It also, another thing we notice here is we can do this crossed design on the suspension system, which basically you can, you know, basically the armature will move as much as the suspension system can flex. So using that cross configuration, you know, I can get a more displacement using a, you know, a same diameter shaker. So it's another way to keep the shaker compact while I'm still getting a lot of displacement out of it. One other thing about the FLEXURE system I forgot to mention is we want it to be soft in the axial direction, the direction of the shaking, but you want the whole system to be very stiff on the transverse direction, because if the suspension system is not stiff on the transverse direction, the armature will jiggle, will have some play, and that's bad because you can easily, if you move the armature horizontally or too much, it may start to touch the edges of the magnetic gap, and you start to have interference, and the shaker won't be able to move up and down anymore. So you want to keep it stiff on the transverse direction, but you want to keep it soft in the axial direction so the shaker can move. And of course, making that armature, that FLEXURE system very robust is key for some of the industrial applications. So here's an example of a portable field instrument. It's our portable vibration calibrator. And in this design, we kept, you know, being a very rugged suspension system is key because it's a calibrator. You're mounting and mounting sensors all the time, applying torque to to the FLEXURE system, so you want that to survive hundreds of thousands of cycles of operation. Okay, so we're going to look at a couple of some other unique designs. One is the air-bearing shaker, which is a special shaker that's used for accelerometer calibration applications. In this particular design, one thing we did, we eliminated the mechanical suspension system completely, not eliminated, but we replaced that with an electromagnetic suspension. So instead of having flexures, we added an additional coil to the armature, and that coil is powered by a DC field supply, and I can control that DC voltage to basically counteract the mass and the weight and the payload of different types of sensors that I'm calibrating. So if you have a heavier sensor, you apply a little bit more of DC on that current. So you can basically control the middle position of the shaker armature, and that helps with the calibration application. The other thing that's interesting in this design is the armature is centered not through a mechanical suspension system, but instead we use a very stiff air bearing around the armature, and that creates an air film with a very high lateral stiffness, which basically translates into a very low transverse motion as the shaker goes up and down. The shaker is only going up and down and almost not having any type of jiggling or any transverse motion that can affect calibration. And that's pretty a common issue with FLEXURE-based systems, FLEXURE-based shakers, but with the air-bearing design, you pretty much eliminate that and keep the shaker under the ISO recommendations for calibration shakers. We also make the armature in this shaker lightweight and stiff by using beryllium as the basic material for this armature versus other types of materials like stainless steel, or that would be not as lightweight and not as stiff. So with the beryllium armature, you can get some very good high frequency performance on this kind of shaker, which is key for calibrating high frequency accelerometers. We're running a little bit out of time, but this is just a comparison of an air-bearing shaker versus a traditional FLEXURE-based shaker, and shows a little bit of the differences in performance and some of the glitches that you would find sometimes on FLEXURE-based shakers that basically are eliminated on the air-bearing shaker design because you don't have as much transverse motion. Last but not least, we're going to look at the low frequency performance. So if you want a shaker that can do very good at low frequency, that can produce higher accelerations at low frequencies, you need to have more stroke. That's key again for some calibration applications where I'm calibrating low frequency sensors. So one particular design uses a linear motor technology to be able to create up to 10 times more stroke than you typically see on a traditional FLEXURE-based shaker. So we can get up to 10 inches or 250 millimeters with this kind of linear motor design. With a FLEXURE-based shaker, we can also optimize the displacement, like we mentioned before, using that cross suspension design, and we can do typically up to 13 millimeters with a small size shaker versus the typical 5 millimeters that you find on shakers that are about the same size. In modal testing and low frequency, that's also interesting. We were able to get 40% more stroke in one of the modal shakers that we offer compared to other traditional modal shakers that have been out there for some time. So I'd like to conclude by just summarizing that, shaker technology is not new. It's been around for many years. And so the basics of how shakers operate and work is still the same. The most important innovations have been, improvements on the design. And a lot of those improvements, were driven by specific applications. New materials definitely have helped improving the design, making shakers more robust, making magnetic circuits more efficient, and also making the performance better for some particular applications. And we continue to incorporate those technologies into our new designs for both shakers and amplifiers. And selecting the right shaker for your application is key for your success. So if you have any questions, please do not hesitate to contact the Modal shop, and we will help you select the right shaker for your application. And with that, I would like to thank everyone for attending today's webinar, and see you next time.